Good morning or afternoon, maybe even 2 a.m. in the morning. All right, we are checking out N46, the last part of electrochemistry. I call this one variables unite. This is when we kind of bring everything together in order to see the relationship of variables and how they affect one another. So this diagram, triangle of death, if you will, should be in the reference sheets. It's a good one to have or get going and keep in your notes. So, for a spontaneous reaction. All right, well, one that proceeds in the forward direction with the chemicals in their standard states. We know this from, again, thermodynamics, as we see delta G, top of the pyramid. So delta G has got to be negative. We know that one. It's not a negative cell potential. It's just the part of the PowerPoint, but cell potential must be positive. And then with equilibrium, again, not a negative equilibrium constant, it has to be greater than 1. All three of these things are going to correspond to spontaneity or spontaneous reaction or process. So we know that delta G equals a negative RT natural log of K, the relationship with Gibbs and equilibrium. We also now see that Gibbs and cell potential are related when delta G equals minus NF cell potential. N is moles. F is Faraday's constant. It's on your equation sheet. As we said, N, number of electrons. F is Faraday's constant. I believe your equation sheet has it as 96,500. So whatever the equation sheet says, that's the constant you want to go with. Coulombs per mole of electrons. Questions on this triangle? Okay, so let's look at delta G and E naught, or cell potential, just to kind of see what's going on. Here's our copper zinc reaction from last time. We know it's cell potential of 1.10 volts. N is the number of electrons in the balanced redox equation. So again, you can balance a reaction. You can see how many electrons are involved. Faraday's constant, again, 96,500, I believe, on your equation sheet. Here's our reaction again. You plug everything in. It's a 2 mole difference of electrons. Multiply it all out, and you get your delta G value, which again should be negative, which of course you could then figure out the equilibrium constant if you wanted. Questions on this little simple calculation? Alrighty then. Brings us to the Nernst equation. This is a little double-edged sword. The Nernst equation has been removed from your equation sheet, which means mathematically you will not be solving it, which is a shame because the Nernst equation is like the foundation of electrochemistry. All parts in here you are familiar with. Now the big thing here with the Nernst equation, as you can see at the top, it allows us to calculate the cell potential when two cells are not 1 molar. Remember, standard conditions is 1 molar concentration. R, energy constant, T is temperature in Kelvin, can't forget that one. Moles of electrons, we just learned about that one. And then Faraday's constant, natural log of Q. So, which means we are not at equilibrium. You want to know what direction we're going to head to get there. So it's still a Q value, not K. A quick derivation of it, kind of see where it kind of comes from. Remember this equation we saw back with thermodynamics. Kind of one way where it comes from. You can look in your book. It may have some more information on the derivation of it. Again, you're not going to use it anymore, but again, sort of understand what are the pieces of it and what controls it. Questions? Alrighty then. So let's simplify some things. We're at 25 degrees, 298, and then Faraday's is a constant, so easy enough. we're going to get this lovely equation, kind of mess around. Honestly, I don't remember how it went from natural log to regular log. On the equation sheet years ago, it was log. So again, yeah, that one was a weird one. I think it's supposed to be natural log, but again, you're not using it for math, so don't worry about it. It's still the same, graph of a log of x. Same thing kind of happens. Questions? Okay. So our goal here is figuring out E of the cell when the ion concentrations are not 1 molar. Now, without even using the Nernst equation, the cell wants to get to having 1 molar concentrations. So based on that simple fact that both beakers here want to get to 1 molar concentrations, you should be able to figure out from that perspective what we're going to do. So the left hand, standard conditions, 1 molar of each zinc and copper ion. The right hand side, we have zinc at a lower concentration than 1 and copper at a greater concentration than 1. So only way to increase zinc concentration in solution is to oxidize it, and the only way to lower the concentration of copper ion in solution is to reduce it. That process occurs, and we know the cell is going to go in the forward direction, as we see here from the anode toward the cathode, to ultimately go until both the concentrations in solution are 1 molar. Questions? Okay. So, equilibrium constants and cell potential. We know that at equilibrium, forward and reverse reactions occur at equal rates. Nothing new there. However, from a cell potential, the battery is dead. Once you're at equilibrium, there's no more flow of electrons. So when your batteries die in your calculator, the little mini cell that's inside those batteries has reached equilibrium, the battery's dead. And if you have rechargeable ones, then you just put them in a charger and you force the reaction in the reverse direction. Electrolytic cells is a rechargeable battery. You're using an outside source, when you plug it into the wall, to force the reaction in reverse. The cell potential, or E, is 0 volts because nothing's moving anymore. There's nothing to measure. We modify the Nernst equation at 25 degrees. We get this. So E is 0. Remember, E naught can be calculated. That's based on the standard reduction potential chart. We still have our 0.0591 over N log, but now it's K. It was Q when you were not at equilibrium, but here now we are at K, or at equilibrium. Questions on this? Okay, so continuing along, here's our zinc copper cell. We know the E naught is 1.10 volts. Plug this lovely thing in to our Nernst equation, or the modified version of it. Rearrange, and then ultimately solve for the equilibrium constant. This is one way of doing it, using the Nernst equation. Again, if you know E naught, you can solve for delta G. You could use negative RT natural log of K. Multiple ways of doing it. But again, College Board's not going to ask you to solve this one. What College Board's going to get into is, like I described earlier, with the different concentration of cells, they want to know what direction is it going to go in? How is equilibrium being affected in that sense? Questions on this calculation that you won't actually do? Alrighty then. So, concentration cell. Both sides have the same components, but at different concentrations. So, 2 zinc electrodes with 2 zinc solutions at different concentrations. We don't know the volts, which we're trying to figure out. So, step 1. We want to determine which side undergoes oxidation and which side undergoes reduction. So, pretty sure most of us can kind of figure out they have to meet somewhere in the middle. I can't make the 0.1 molar zinc go less, and I can't make the 1 molar zinc increase. They have to meet somewhere in the middle or go in that direction. So the 1 molar zinc must decrease and the 0.1 molar zinc must increase. Hopefully that's pretty straightforward. Any questions on that idea? Okay. So we get this reaction, as in, or half reaction. The zinc with the 1 molar is going to be reduced. There's my cathode. The zinc of the 0.1 molar is going to be oxidized. There is my anode. So I know what's going on either side of my lovely cell. So I'm going to get zinc 2 plus going to zinc 2 plus, but our concentrations are different. Questions? Okay. So moving on, step 2, calculate the cell potential using the Nernst equation, assuming 25 degrees. Well, we know this to be true. Here's our equation. Notice, we're not at equilibrium, so it's Q, not K. Continuing along, E naught's going to be 0 because it's the same thing being oxidized and reduced. So the two half reactions are identical but opposite sign. Hopefully that's clear. We know it's 2 electrons in the transfer. Q is this. So this is where it comes into of you guys using the Nernst equation conceptually. You need to know what's going on with Q, because once you know what's going on with Q, you can figure out if E naught, it's 0. So conceptually, is my value of E going to be greater than 0 or less than 0? This works really well, and from an explanation or a justification perspective, it also supports what you're trying to say. So you need to know the Nernst equation conceptually inside and out. Plug everything in, and we get our positive 0.03 volts. So this cell is going to produce very small amount of volts in order to get to equal concentrations on both sides. Questions on this? Okay. All right, brings us to our electrolytic process. As I have mentioned a couple times, electrolytic is non-spontaneous. Notice right there at the top of the image, you have a battery. This is a rechargeable battery. Next thing to notice, the negative side and the positive side have not changed. Negative on the left, positive on the right, as you can see right there. Right there. Next thing to notice, the electron flow is going in the reverse direction than what we have seen. Third thing to notice, and probably the most important part, the anode and the cathode, where they're taking place, have switched. Remember, the anode is where oxidation takes place and produces electrons. The cathode is where reduction takes place and uses electrons. Notice the electrons are going towards the negative side of this cell. Negative electrons going towards a negative side. That shouldn't happen, and that will not happen spontaneously. But if you have an external source of power, a battery, or you charge with your wall, you can force the electrons in the reverse direction to recharge your battery. We get a negative cell potential. Well, if I get a negative cell potential, I have to have a positive free energy change. Non-spontaneous process. Questions on this? Okay. So, in all electrochemical cells, oxidation is always the anode, reduction is always the cathode. That doesn't change. In voltaic cells, we know anode is the source of electrons and has a negative charge. Cathode draws those electrons and has a positive charge. Just like the battery, the little cells we have seen the whole time. The anode was on the left, the cathode was on the right, where the negative and the positive were. Remember, voltaic and galvanic are the same thing. With electrolytic cells, electrons are drawn off the anode, so it must have a place to release those electrons, the positive terminal of the battery. The electrons are forced towards the anode, so it must have a source of electrons, the negative terminal of the battery. So, image coming up here in a second to kind of show a little bit of a difference. Questions on this? Okay. So, left-hand side, voltaic cell, we've seen this a bunch of times. Anode left, cathode right. Electrons flow from the negative side to the positive side. On the right-hand diagram is our electrolytic cell. There's a voltage source greater than 110. So it's greater than what the actual normal thing would be. The electrons are going from the right towards the left. The anode and cathode have switched sides, as in the place where oxidation and reduction are occurring. Notice the positive side of the battery is on the right, the negative side of the battery is on the left. The electrons are going towards that negative. Big differences here with voltaic / galvanic versus electrolytic. Questions? Okay. All right, our friend electrolysis, the process of using electrical energy to break compounds apart. Most people are familiar with the electrolysis of water. H2O, break it into hydrogen and oxygen. You get double the amount of hydrogen gas because of the ratio of 2:1 hydrogen to oxygen. Electrolysis is an electrolytic process. It's not going to happen on its own. You have to force it with an outside source. But it is useful to separate elements from a compound. Just a bigger version of it so you can maybe see it better. Alrighty then. All right, continuing along with the electrolysis of water in acidic solution. Don't worry about that aspect. Everything in College Board is in acidic. So the anode half reaction has that value. The cathode half reaction has this lovely value. You add it up, you get water going to hydrogen and oxygen, which is what we're producing, and you get your cell potential. Notice it's negative. You are forcing this to happen. Questions? All right. We will finally reach almost the end with electroplating. That's the goal, is to plate something with another element. So in this one, again, notice right there, source of current. So electroplating is an electrolytic process. My anode reaction is I'm taking silver to create silver ion. My cathode reaction is I'm taking silver ion to make silver. I have to have a source of my element that I want to plate in order to make this work. So we need a solution of plating material. Makes sense. We need an anode made of the plating material to produce more of it as it is used up. And we need a cathode with the object to be plated, what we're going to put on to it. And then you need a source of current. You need a battery. You need a plug. You need some power supply to make this thing work. Questions? Alrighty then. So, electroplating. Pretty straightforward. The working piece is the cathode, where you're actually making it produce that solid onto a material. Cations are reduced at the cathode, we know this one, and plate to the surface of the work piece. In class, if we had a chance to do this, I usually get a key from like Home Depot, like a brass key or a silver, or kind of a silverish looking key, and we plate it in copper. So we have a copper solution and we have copper electrodes. Make it work. So from our little diagram here, we have our oxidation and reduction. Again, notice the electrons are flowing towards the negative side of the battery. And then we plate that lovely ring, whatever it looks like, with some silver, solid silver. Questions? Now, from electroplating, this is the process, but we have to solve the problem. There's two ways to usually solve the problem. Number one is how long will it take to plate out 5 grams of silver, as an example. Or it could ask you, how many grams will be plated? Those are the kind of the two main questions we're going to kind of look at. For this one, we're solving for time. So we know silver ion becomes silver. So I take my 5 grams and divide by the molar mass. Got to get moles. Everything goes to moles. We know this. Stoichiometry rules the world. Then I have to multiply by the number of electrons in the process. So in this one, silver is being plated with a reduction of 1 electron. Easy enough. Then it brings into Coulomb's law, because we know that current and coulombs are related. So coulombs per 1 mole of electron, that's going to cancel out. And then we know our time is 1 second, or 20 coulombs, because amps is coulombs per time. And we're solving for seconds. Cross it out, and then we get 2.2 times 10 to the 2 seconds to ultimately plate out 5 grams of silver. Now realize, if you are solving for mass, you would just go in the reverse direction. You would use your amp current, and then you would just work your way back in the reverse direction to solve for mass. So you got to be able to go in the forward and the reverse direction. This type of problem, FRQ all over it. So if electrochemistry, not on the AP exam, you don't have to do this. Any questions on electroplating? Alrighty then. Well, I think we are done. Yes, we are. Until next time. Bye-bye.